Energy time! Jump! Okay, so we have talked about work so far in this class and in these videos. Work is a force dotted with some displacement. So we've had like F dot delta X or F dot X or F dot D, however you want to think about that, or whatever letter you want to use there. But it's some force dotted with a displacement. And that really means that that force is acting on some object in order to cause it to move. And we care about the force vector component that is in the same direction or on the exact opposite direction, whatever's parallel to the direction the object's moving. And we saw how we could have works or forces pushing an object forward for a positive work, forces acting against an object for a negative work. Hint, hint, that was on one of our quizzes that came up. Or if a force is acting at 90 degrees to an object's displacement, that work is zero, because that cosine component that pops up happens to become zero there. What we're going to look at here is this idea of energy. And you may have already talked about energy in some of your prior science classes before. You may remember some of the terms we're going to talk about today. But while we're looking at energy here, we're also going to look at how it's related to the idea of work that we've been discussing before this. So let's kind of dive into this and see where it takes us. When we think about energy in general, we're going to use the symbol capital E for an energy. And note that this capital E, it does not have a vector arrow over it or anything. It is a scalar amount, but it could still be positive or negative. If you end up looking into electrostatics next year in AP Physics 2, capital E with a vector over it is actually an electric field. So make sure you don't write that. That's a different thing, because physics has to be confusing for us for some reason. Couldn't pick any different letters. But anyways, energy, a capital E, it's the ability of an object or a system to do work. So if something has energy, either a stored energy or it has the energy at that moment, then it can do some useful work. And that also means that if we do work in an amount of time, we know this as being power. So it's an ability of an object to do work, and therefore we can get power out of it as well. And because it's just the ability of an object to do work, it should have the same units as work. So in our English system, we're going to have these weird foot-pounds again. But in our proper metric, our SI, System International units, we're going to have joules, our standard unit of energy, or if we wanted to, we could write that as a Newton meter. So if you wanted to write that as a Newton meter, you could as well. So that's what we're looking at here. We can see that energy and work are going to go hand in hand. They are one and the same, or they can be transferred back and forth in that idea for what we're looking at. Now, there are a lot of different types of energy. When we think about all those, they come down to being this kinetic energy and a potential energy. We are going to only focus on the kinetic energy aspect right now. We're going to come back and talk about potential energy later, because potential energy can go into all different worlds here. We can go into static electricity in AP Physics 2. We can talk about hills where we can gain potentials. There's all sorts of different potentials out there that kind of merit their own little subspaces, even to the point where, like, if you pull back a slingshot, you've stored energy in the slingshot rubber band, or if you're pulling back a bow and arrow, you're storing energy in both the curvature of the bow and your actual chord or your line there. So there's lots of different potential energies, but when we talk about them, they'll each have their own little subpart. We're just going to talk about kinetic energy right now, because we're going to see how it very much ties us into the idea of work. So when we talk about kinetic energy, like I was talking about with that old Xbox Kinect, it is the energy of motion. And we abbreviate it with a capital K. Sometimes we'll abbreviate it with a KE. Sometimes that works a little bit better for us. But we have some kinetic energy here. Now, this kinetic energy, the energy of motion, means that an object must be moving to have this kinetic energy. An object must be in motion to have kinetic energy. So we kind of break this down a bit more. If an object is moving, it has the ability to apply force on something. Think of like a bowling ball going down a lane. When it gets to the end of the lane, it's going to apply a force on those pins. And it's going to, boom, shoot the pins to the back. If it applies a force on another object and that other object can move, then hey, look, we have a force and a displacement. We have a work. That work was only done because one of our objects was moving. Okay? So that's what we're really thinking about with kinetic energy. Mathematically speaking, we get this idea of kinetic energy from our work equation. And it's a little neat how we get it. You don't have to copy every single step of this down. I'll tell you what you need to box. But here's how we actually get kinetic energy. And if you had enough time, you could work this out. We start with F dot x, which remember was just Fx cosine theta. Now we're going to just pretend here that the direction of the force and the direction of the displacement are in the same line. And if they're in the same line, then the angle between them is 0, and the cosine of 0 is equal to 1. So we're just going to get rid of this cosine component real quick, because it's just going to be equal to 1, and anything multiplied by 1 is just whatever that thing was, right? So, boom. There goes the cosine. So we have work equals force times the displacement. If we recall, though, back in Unit 6, we learned that F equals ma, Newton's second law. A force equals a mass of an object multiplied by an acceleration. So let's substitute ma in for F. And now we have work equals max. A mass times an acceleration of that mass multiplied by the displacement of that mass. But we might also remember that we have motion equations from units 2 and 3. Those were our best friend sheets, equations 1, 2, 3, 4, 5, and 6. If we went there and we pulled equation number 6, an equation that didn't have time in it, we could say the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. And if we kind of worked this equation around to solve for the acceleration, we subtract the velocity squared to the other side, and then we divide by 2x, we can take this large piece here, this v squared minus v squared over 2x, and we can put it in for a. So when we do that, we have this large term here. But what we might notice here is that these x's have divided out, and since both the vf squared and the vi squared are divided by 2, it's actually a little easier to pull the 2 out front as well, or should I say the 1/2 out front. So what we end up getting here is that work equals 1/2 m times the final velocity squared minus 1/2 m times the initial velocity squared. This 1/2 mv squared, this is the energy of motion. This is kinetic energy. Box that on your right-hand side box. That is the energy of motion. So when we talk about kinetic energy, like what is the kinetic energy of a baseball as it's thrown? You need the mass of the baseball, and then you need the baseball's speed. 1/2 mv squared. We actually don't care about what direction that baseball is moving. Forward or backwards, it doesn't matter. This is a speed. And as a result, kinetic energy is either from 0 or a positive number. It cannot be less than 0. Kinetic energy always has to be greater than or equal to 0. You can't have a negative kinetic energy, because if you're walking backwards, you still are moving, and therefore you have kinetic energy. So your kinetic energy always has to be a number greater than 0. Always. Okay? Either 0 or a number greater. You're either not moving or you are. Now, we can then, if we've used work to get to energy, we can then create a work energy theorem. In general, the work done on an object is equal to its change in kinetic energy. So Andy right now is sitting in one of our wheelie chairs. If I do work on him, I exert a force on him over some sort of displacement, he will speed up. We can say then that this work, which equals 1/2 m vf squared minus vi squared, we can just state in general that work is equal to the final kinetic energy minus the initial kinetic energy. And if we wanted to write this in a full blown out term here, this is what we would have. I like to put the final minus initial down here because remember, that is what a delta is. When we say delta K, we are saying final minus initial. And then that final equation at the bottom is that work equals 1/2 m vf squared minus 1/2 m vi squared. It's also helpful to remember, and I like just to put it here as well, that this work equals a force dotted with a displacement. That's an important thing to remember. That work, we can't just say it's work. It is a force and a displacement dotted together. So that's something to keep in mind as well. Okay? So that is our work energy theorem. That is what we're thinking about there. That is how we can push on an object with some force over a displacement and understand that, hey, now that it is moving and it has some speed, it has some kinetic energy. In our next little video, we'll take a look at an example of how we can use this work energy theorem, and then we'll start taking a look at some practice problems to this. But until next time, adios, take it easy.